Aradhna Singh.
And I'm Ayush Kumar Singh. We are delighted to be the co-host for this momentous occasion.
It is our immense pleasure to welcome you all to the grand inauguration of IEEE Geoscience and Remote Sensing Society Student Chapter here at Bengaluru.
We are honored to have such a distinguished gathering to celebrate this significant milestone in our institution's journey.
To begin our ceremony, I would like to invite our dignitaries onto the stage. Our chief guest, Dr. SACHIDANADA BABU from NASA, Dr. Jagannath Karodi, Director of MIT Bengaluru, Dr. Ujjwal Verma, Head of the ECE Department at MIT Bengaluru, and IEEE GRS Student Branch Chapter Faculty Advisor, and Dr. Balachandra Achar, IEEE Student Branch Advisor of MIT Bengaluru.
We will now start the event with our convocation ceremony. I would like to call upon Ms. Sri Lakshmi to start the invocation.
Ya kundendu tusharahara davana Ya shubhra vastranvita Ya veena varadanda mandita kara Ya shweta Padmasana Ya Brahmachuta Shankara Prabhriti Devai Sada Pujita Shama Patu Saraswati Bhagavati Nishesha Jadhyapaha.
Lighting a lamp at Indian inaugurations symbolizes dispelling darkness and invoking blessings for auspiciousness and unity. I now invite all the dignitaries present on the stage to light the lamp.
Next, we pay tribute to Dr. T.M.A. Pai, a visionary educator and a philanthropist who transformed the landscape of education and healthcare in India. As the founder of the Manipal Group, his relentless dedication to creating the world-class institutions has left an indelible mark, providing countless students with opportunities for excellence and fostering a legacy of innovation and compassion. Let us take this moment to dedicate a floral tribute to him.
now I call upon Jagrut Palakonda, the chair of IEEE GRSS SBC of MIT Bengaluru, to present saplings to our dignitaries. Our chief guest, Dr. SACHIDANADA Babu, Technical Program Manager, Earth Science Technology Office, NASA. Dr. Jagannath Karodi, Director of MIT Bengaluru. Dr. Ujjwal Verma, Head of ECE Department and Faculty Advisor of IEEE GRSS. Dr. Balachandra Achar, Faculty Advisor of IEEE SB.
Jagrut will now introduce IEEE GRSS Student Branch Chapter here at MIT Bengaluru.
Thank you, co-host. That was very nice of you. Ladies and gentlemen, distinguished guests, esteemed dignitaries, and my fellow students, good afternoon. It is with great pleasure and excitement that I stand before you today to extend a warm welcome to each one of you to the inauguration of the IEEE Geoscience and Remote Sensing Society Student Branch at Manipal Institute of Technology, Bengaluru. This marks a significant milestone in our journey towards advancing the field of technology, and I'm thrilled to see such a diverse and enthusiastic gathering here today. The IEEE Geoscience and Remote Sensing Society, GRSS in short, is a premier global society that brings together professionals, researchers, and students dedicated to advancing remote sensing and geoscience and technology. Our society's interests span a wide range of areas, including remote sensing of the Earth's land, oceans, and atmosphere, analyzing and interpreting remotely sensed data, and developing algorithms and techniques for environmental monitoring and modeling. The IEEE GRSS is dedicated to the development and dissemination of knowledge and technology in the areas of geoscience and remote sensing. Our mission is to foster an environment where innovation, collaboration, and education can flourish, providing a platform for researchers, professionals, and students to come together to share their expertise, ideas, and passion for this dynamic field. Today, we embark on a new chapter that promises to bring numerous opportunities for learning, growth, and collaboration. As we look ahead, I am confident our chapter will significantly contribute to the Geoscience and Remote Sensing Society. Together, we can drive innovation, address global challenges, and make a lasting impact on our society and the environment. Once again, welcome to the IEEE GRSS chapter at MIT BLR. Let us embark on this journey with enthusiasm and a shared commitment to excellence. Together, we can make a difference and contribute to advancing geoscience and remote sensing for the benefit of all. Thank you.
Thanks for that, Jagrut. Now I'd like to call upon our chief guest, Dr. SACHIDANADA Babu, for the virtual inauguration, along with our dignitaries.
Next, I would like to request the Director of MIT to hand out the official appointment letters to the office bearers, and I'd also like to invite our chair, Jagrut Palakonda, who is currently pursuing IT in his second year at MIT Bengaluru, to receive his official appointment letter.
Thank you. I'll take it here from now. Now I call upon our Vice Chair, Ayush Kumar Singh, a second-year student pursuing computer science and engineering specialization in artificial intelligence. Our Treasurer, Aradhna Singh, is a second-year student pursuing computer science and engineering specialization in data science. Our webmaster, Abhijit Pai K, is a second-year student pursuing electronics and computer engineering. Our General Secretary, Sampreet Byali, is a second-year student pursuing computer science and engineering. And our Executive Head, Srujan Kumar Chilveri, is a third-year student pursuing computer science and engineering in specialization computer cyber security. I'm confident in my team, and I'm sure that they'll take. I'm confident in my team, and I'm sure that they'll take the IEEE GRSS Student Branch Chapter MIT BLR to greater heights. Thank you.
I would now like to introduce Dr. Jagannath Karodi, the Director of Manipal Institute of Technology, Bengaluru. Dr. Karodi has over 35 years of experience in technical education, including roles as Dean of Faculty of Engineering at Manipal University, Jaipur, 2019 to 2022, Associate Director for Alumni International Relations at MIT Manipal, 2009 to 2014, and Head of Mechanical and Manufacturing Engineering Department at MIT Manipal, 2016 to 2018. He has published over 75 research papers, reviewed more than 20 PhD theses, and is dedicated to contemporary curricula and outcome-based education. He is also a member of several professional organizations and editorial boards and has organized numerous conferences and workshops. I would now request our Director, Dr. Jagannath Karodi, to come to the podium and share a few words on this auspicious event.
Thank you. Good afternoon, everybody. I don't take much time because we are all very eager to hear from the great scientist from NASA we have today. Respected chief guest of today's function, Dr. SACHIDANADA BABU. He's Earth Science Technology, NASA, one of the very prominent laboratory from which he was telling me many things have gone to space from there because of his and his team's efforts. Such a person is here today with us. It's a very pride occasion for all of us, and we should listen to him more than anybody else. I also take this opportunity to welcome Mrs. Geeta Sachidanand, who is also with us today. She is also an engineer. She is a she has done masters, electrical engineering, and then she has done MBA. Very high scholar, and she is also working in USA. Thank you, madam, for coming also along with your husband. And also I'll take this opportunity to welcome you all, my colleagues, Dr. Ujjwal, Dr. Balchandra Achar, Dr. Ivan Jose, and all my faculty colleagues, my dear students. It's a special occasion for all of us. And one of the prominent society in MIT Bengaluru, IEEE, Geosciencing and Remote Sensing Society, they have organized this function. And I am We have more than about, now I think have reached more than 40 clubs we have. Name it, whether it is technical, cultural, community service, VSO, NCC, NSS, you name what it is there. All these clubs are formed because of the students' interest. They are all student-driven clubs. And each club is having faculty advisor, and they are doing lot of activities throughout the year. I am very proud of my students. They are all very talented. And this is one such event we are organizing. And this particular event, especially a scientist, a great scientist has come to our organization. What is the significance? You are all going to become engineers. There is always a struggle or war between scientists and engineers. Who are more or who are above one and all? Scientists say they are, and engineers say we are. But I say both are. Because science is all about knowing, whereas technology is all about doing. Without knowing, you can't do anything. Even if you know everything, if you don't do anything, that will not help the society. So both of us, scientists and engineers, should work together. They cannot be separated. And when earlier during my engineering education, we have not heard of research. And even when I joined the Manipal Institute of Technology, Manipal, it was just like a teaching institution. All institutions were just teaching, including IITs at that time. But the time has changed so suddenly, so drastically now. Our own students, many of our students, along with their academics, they want to go in the research area. They want to publish papers by doing projects along with the faculty. And this was not there earlier. This opportunity was not there for us. And you have got this opportunity and you have to make use of it. When engineers become scientists by doing research, it will take the society to a new level. Because all these inventions, what the scientists do and engineers apply it, will help the society, will improve the standard of living of people. But this, when an engineering student pursue masters and then PhD, then goes in the research area, he will be or she will be much more capable, or rather than a pure scientist or a pure technician, in my opinion. So this is an occasion for you all to listen to the great scientist. I don't take much time. So welcoming you all again, and I wish this function a grand success. Thank you very much.
Thank you, Dr. Karodi. Your words have never failed to inspire us.
I now call upon Dr. Ujjwal Verma, Head of the ECE Department at MIT Bengaluru and Faculty Advisor of IEEE GRSS, to introduce our chief guest.
Good afternoon, everyone. We have with us today Dr. SACHIDANADA Babu, who is working as a technology program manager at the Earth Science Technology Office of NASA, USA. He completed his education in physics, electrical, and computer engineering from University of Mumbai, George Mason University, US. Later, he joined NASA Goddard Space Flight Center as a detector systems engineer way back in 1989. He has spent more than 3 decades, 35 years to be exact, at various capacity in NASA. He has been instrumental in the Landsat mission 8, 9, and right now he will be sharing with us some of the experiences that he had in these missions, and I hope that will be really useful and inspiring for our students. He is also actively involved in the IEEE GRSS Society at a global level. He is a working group lead for remote sensing instruments for small satellites of the GRSS Technical Committee on Instrumentation and Future Technologies. So with that, I request SACHIDANADA Babu to take this over.
Thanks for all those kind words. I'm just another person like you all started studying the same. We all start the same way, like students, and grow up to become an engineer or a scientist. But what is most important is the dedication and the hard work that you all put into it. And you should always have hope and optimistic, because there's always problems, and you should not look at as a problem, but it is a teaching tool for you. Every problem teaches you something new, and use them as something that is useful for you in your life. So with that, I want to give some small idea about what is it that GRSS can do. What is it? Some of you may know what is remote sensing. Some of you may not know what is remote sensing. I'll give few introductory slides to show that, and also to show that when you see a big satellite mission, you don't realize that how much work has gone behind that. Starting from a simple thing like a small part has to be developed, and how the development takes place and how it evolves over time. This involves both sides of my work that I have done in NASA, having worked on building big missions, satellites like James Webb Space Telescope, which is the biggest, and the smallest ones like these CubeSats that we have launched to do Earth observation. So the whole spectrum of it, I've worked over the years, and I'll give some, at least a flavor of it, that you will see what has been done. So you see this, when you see an Earth, the first one that you see, there's a blue marble, we call it, that the very first picture that Apollo astronauts took, the picture of the Earth, that was a blue marble, because that became a very famous Earth picture. Then we started realizing that it's not a simple, Earth is not a simple matter. It is very complex. And that is when we started looking at air, water, ice, land, life, everything. So, and solar, what is it? Sun is affecting Earth. So it's a very dynamic situation, and it changes every second. So how do we study this? The best way to study is from space, of course, but there are many ways to study Earth. Remote sensing, when somebody says remote sensing, don't get the idea that only you have to have a satellite and you have to do the study from satellite. It can be a simple thing as a drone, an aeroplane, a balloon, or a satellite. So when somebody comes and tells you that, oh, you have to have a satellite to do something remote sensing, don't get that kind of an idea, because try to see how you can do, try to think, how can I do something here? Because sometimes you may not be able to do everything from space. So in Earth Science Division in NASA, we have multiple things. As you can see that we have a cycle where we have bottommost, as you can see that the technology is the most important thing. Technology, missions, and data. These are the most important things. Those form the core of the whole system, a pyramid. And bottom of the pyramid is the most important part of it. And then above that, you have applied research, science and applied research. When you have technology and missions which bring the data, you use the data and you start analyzing it and you start coming up with ideas. A couple of those next few slides, I will show you how it can help in everyday, day-to-day life. So what we do in NASA is most important thing is that we innovate and integrate the data and then inform the public. That's the most important thing. It's the same philosophy that Indian Space Research uses, and it is every European Space Agency. Everybody uses the same thing. What is most important is that just collecting the data is not the only purpose. Analyzing the data is not the only purpose. You have to be able to put it into action. What is the action? Action is to inform the people, and people should know. So in NASA Earth Science, we have, you can see that the number of satellites that we have, all the way from Landsat 7, it goes to Sentinel, the next generation, Landsat Next, that is the next mission that we are developing. And on the side, you see here, there is CubeSats. So all these are bigger satellites, whereas why do you have these small satellites here? So we have these small satellites to develop technologies and then validate them in space. There are some technologies you cannot validate them on Earth, and some measurement techniques you cannot validate them on Earth, but you can validate from space. So we validate the technology from space, and then later that get into the bigger missions. And you will see some of the examples of that also. So look at this. This is the kind of data that NASA produces. This was the ocean chlorophyll, this blue is, all this, and then the land vegetation. So we look at the vegetation. As you can see here, Sahara Desert, there's no vegetation at all, whereas there's quite a bit of vegetation here. In fact, one of my colleagues, we keep joking with him. He recently finished counting the trees near Saharas. His greatest achievement was that he took the data, satellite data, and went with the artificial intelligence, machine learning, and he was able to count all the trees. Now we have given him a new assignment, count all the bushes in Australia. So he's working on that. So things like, see, you always have fun. It is not just, when you do the science, it is not just science. You should think that as a fun. And another important thing is that PACE. PACE mission we launched recently on February 8th, and this is very important mission. Why, you might ask? This measures the ocean color measurement. Why is ocean color so important? Ocean is where there are a lot of phytoplanktons. Phytoplanktons are the ones which generate close to 60% of the oxygen that we breathe today. If they don't exist, if they don't produce the oxygen, Earth will not be habitable anymore. So we have to look at their health, and we have to see how we don't affect their health. So remote sensing comes in very important there. So you can see here, this is the color. You can see that chlorophyll, all these things. This was a picture that was taken by PACE spacecraft, and you can see the color differences, how you can classify different phytoplanktons and chlorophylls and things like that. And this is one interesting one, phytoplankton bloom in Gulf of Oman. You can see that how green color this is blooming. That means that it is producing a lot of oxygen there, and that is what is needed for us every day. So as you can see, that a most important thing that we have to do is that connect it to human life. When we do any of this remote sensing, how do we connect it to everyday life? How do we make people understand what they are doing is right or wrong? Because we have to guide the people. When you go and tell people that, oh, don't use the petrol engines, that is putting a lot of this carbon dioxide and all this, oh, it is creating global warming. Person will say that, hey, that is my livelihood. Why are you doing this to me? What is good for it? Then you have to educate that person why you need to do that. And how do you educate? Remote sensing is the one as a tool that you can use. Look, here is the data. Here is how it shows. So to do that, we need space missions like this, and people like Ujjwal and others going and doing the analysis and teaching you all how to do the analysis. The data is available. NASA produces so much data that it is freely available. like Landsat 8 and 9 I worked on, all that data is available. PACE, this data is all available online. And all of you have to use that data and analyze it and tell the story why it is needed. And for example, this is again PACE imagery taken from OCI instrument. In fact, I was part of building this instrument. I was part of the team that we put together this instrument. And same thing, you can see that how different areas, different colors, these colors mean what is the composition of that particular location. So you have to look at composition of the place and then see how it is changing over time. And since these satellites take data continuously, you can always analyze this data. And as you can see that the link is given in the bottom here. You can go to that link and you can see yourself these pictures. And you can, latest data you can see there. And next one is SWOT. SWOT is very important because ocean surface water topography measurements. And this is another one of the missions that NASA recently launched, and societal needs, how the ocean level is increasing, and also the waves that are in the ocean that are safe to navigate or not, those kind of things you should, to measure those things, we have SWOT mission. And if you go to Earth Information Center, which is the web address is given here, there's a live Earth dashboard. You can go to the live Earth dashboard and see what is really happening, what data is telling. And it is your story to tell after that. You have to come up with a story and you have to convey the story to others because you are the ambassadors and you need to take that message to the society. That's why these student chapters are very, very important. Students, you need to take it to your generation, and my generation is already coming to an end. Like Dr. Jagannath, our generation is at the tail end, but you all are starting now. You need to take the message. You need to tell, because not everybody on this campus, even on this campus, not everybody understands remote sensing. They don't know what is remote sensing. You need to go take the message and tell other friends, hey friends, this is what is happening. Look at this. That is how you create the awareness. And as you can see in NASA, we have total of 9 themes and 1 Earth: sea level, wildfires, water resources, and these affects also agriculture, air quality, biodiversity, disasters, and sustainable energy and greenhouse gases. These are very, very important subjects, and we combine all these 9 into 1 Earth, where you can go to the website earth.gov and you will be able to see a lot of this. I just taken some of the data from earth.gov and I'm showing you. And this is to encourage you to go to that website and do some venturing into exploring that yourself and understand it. And you can see here, this is an interesting one, liquid versus the frozen precipitation. You can see that this in the equator and all this, all these parts are frozen, liquid precipitation, whereas you can see near the Antarctica and all, there is frozen precipitation. So like this, we have data that shows that whether it is a rain or it is a snow, what is coming down. That also, that kind of data also. So, and then we have rainfall anomalies. Means, like for example, now these days there's too much rain here, and some places there's no rain. So you can look at the whole Earth, and you can see that some places there is more rain, some places there is no rain. Like for example, here you can see in this chart, the bubbles tell you that whether it is wet or dry, and blue is wet, and the green is the grayscale is all the dry. And you can see that there are places, although there is a place where there's a lot of rain, very next to that there could be dry place. And why it is important? Because agriculture depends totally on water. And that tells you how much agriculture production has happened. And that tells you what is going to be the supply of the food, how much food we are going to get, supply or not. And this is very important because this is something that Ujjwal can explain to you better than me, is the southern Brazil flooding. This is a satellite picture. And the worst floods in 80 years that killed about more than 170 people and displaced almost 600,000 people. That's 6 lakh people it displaced. But we were able to look at it from space and see what was the extent of the damage. You can see that the rivers that are swollen with water and how it displaced the people and all that. And these kind of things, when a disaster happens, we at NASA get a call from different disaster relief agencies for the data. And we supply the data to them and tell them that where the effect is worse, so that the disaster relief agencies can go there and get the relief to the right places. You can see that same thing, US Space Force and Southcom, that is the Department of Defense, they all took the NASA data and then they went and helped the people there. Flood extent mapping, so we do the, like I just said, what is the extent of flood, where there is more flood, where there is less flood, and where there is a major disaster, where it is relatively not that bad, so that you can target the relief effort to the right places. As you can see here, how the flood has swollen the river has become wider, and those things we can measure this here, and this is same Brazil. And then landslide. The next comes after the rains is landslide. And you hear that all the time here, even in the Western Ghats, all the time. The landslide happens. So the best way to study or get the early understanding of landslides is again satellites. In fact, I was talking to somebody the other day. They said that recently during the landslide, one of the trucks got embedded inside the landslide, and they asked for the remote sensing pictures from ISRO. So you can see that the data that is collected from space is so valuable. And this is LASA, this is again Rio de Janeiro, the disaster management. NASA had to go there, and then we had to engage with the local people and tell them where the damage extent is very high and where it is less, so that they can send more aid to the places where there is a lot of damage. And exactly same thing was done when Nepal earthquakes happened. NASA had to supply the data, and we have SAR data, we have visible data, we had infrared data. All this data is put together, and when you combine all the data, you will be able to get a much better picture. And weather. So next comes, apart from that, we have to worry about weather. Weather keeps changing. So we also study weather, how weather is changing. That's why I said that when you go out of here, try to, when you get your spare time, want to read something interesting or look at something interesting, go to earth.gov and see where there is a lot of weather anomalies are happening, whether there is a flooding is happening. Those things you can go and see yourself. And you want to be your own scientist. You become a scientist and see what affects it's the whole environment is changing, and how you can study that. See, one thing we have found is that this is something that I learned when I was way back in '88 when I was in Intel, working with Gordon Moore and Robert Noyce. one of the things they said is that if you give a problem to an expert, he'll be spending a lot of time worrying about too many things because he has already preconceived ideas. He's trying to solve that problem with his own ideas. But whereas you give it to a rookie who is first coming, he has no idea. He will go into wild thoughts and he may come up with the best solution. That's why you people are all most important than any of us who are experts. Same again, air quality, that's very important because you hear every day in Bangalore how air quality is. And in fact, there are, I've seen on the road a couple of places air quality monitors are there and the big display boards are there. So this is very important. We study from space. This is a micro scale, or we study in a universal scale, how it is changing. And on that, it is very interesting. You see here, there were fires that happened in Canada. How the smoke, in fact, I live in Washington, D.C., and last year, there were about at least a week, about 5 or 6 days, we could not go out. That bad it was. It's so far away. It is about 4,000 miles away. Still, the smoke was coming there. So, what better way to study that than space? We study that from space. And Greenhouse Gas Center we have started, and under same earth.gov. And Greenhouse Gas Center is a collaboration between NASA, the National Institute of Science and Technology, and NOAA. NOAA is the weather forecasting agency for NASA. And we are now starting to work with ESA, European Space Agency, and the Japanese Space Agency to form a worldwide greenhouse gas center so that we can look at whole Earth as a one system. How greenhouse gases, these gases don't have any boundary. They travel between Pakistan and India. There's a lot of burning of the sugarcane fields in Pakistan that all that soot comes into New Delhi. So they don't have border. You can't stop it at border. So we have to have a universal view. So we have anthropogenic greenhouse emissions. We do that. We study that. And new observations and tracking. Like we have a new satellite called EMIT. EMIT is a hyperspectral imager, and it looks at the methane and gases like that. When there are gas wells which are not capped, they will be emitting the methane gases. That you can detect those. Those are important because we have to control the gas emission. And same thing, carbon dioxide. You can see that the source and sinks, how the sources are at different places. And fire, this is becoming a bigger and bigger problem day by day. At one point, California used to have fire season, but now every season is a fire season because of the global weather changes. And in fact, we were, Ujjwal and we were in, recently we were in Greece, and Greece had a lot of problems in wildfires. But what I heard was very disturbing because a lot of those are arson, it seems. So the wildfires can cause a lot of problem for your breathing, air that you breathe. So we can look at them, and this particular thing, fire weather index, we have satellites which measure the soil moisture, which measure the temperature of the air, and then how much of a rain has fallen. From those kind of data, we can tell that whether there is a probability of a fire happening in near future. And that is very important because we need to be able to control the fire. These are climate, this again, when you go to the earth.gov, you can see the vital signs, how Earth vital signs, you can look at them, land temperature, anomaly distribution and things like that, how it is changing over the years. In fact, 2023, we had the highest temperature, but 2024 is not, it doesn't want to give up the record. It wants to have, 2024 is going to be record temperature, and that is not helping many of us because a lot of people, like, even in terms of the health, people don't realize that, oh, so what, temperature is becoming warmer, so what? But a lot of people have asthma and other problems, they increase with these kind of things. So when you have health problems, that affects the productivity of the society, and it affects the whole society. We need to be careful to control the weather. And this is again global changes, human and this thing based on GIS model. And again, the crop yield, like I said earlier, we need to be careful about that. And you can see that when you go to earth.gov, you can see the whole, not only one measurement, but every measurement you can see over the years how it has changed. And that will give you a better idea on how to control it. So what is NASA doing now for future? We had satellites till now, and the satellites are there in space. What is the future satellites are going to do? We have surface biology and geology, surface deformation and change, mass change, and cloud convection, precipitation, and aerosols. These are both combined together, aerosols and this thing. So NASA is now coming up with the next generation of satellites, which are going to make these 4 important measurements. Because we have been doing this for so long, we have big, long record, we want to keep making measurements further. So SBG is now in phase A, and right now surface deformation and change is temporarily paused because we are working on NISAR. NISAR is going to be part of the surface deformation and change, which is a SAR, and in fact, Ujjwal knows this very well about if any of you have any questions, he is the best person to answer that. And GRACE is a mass change, and you'll start wondering, why is mass change important? In fact, mass change, this particular mission, GRACE-C, right now is in phase B, but the earlier GRACE missions were able to predict the groundwater depletion. And groundwater depletion, especially in India, in Punjab and areas like that, is so bad that you have to keep drilling the well deeper and deeper, because we are exhausting the water and water table is moving down. So this GRACE mission, mass change mission, can easily estimate where the water depletion is happening and where water surplus is happening. Because when somebody comes and tells you that, oh, NASA is going to do a mass change mission, so what? What is it going to do for me? But this is how a lot of these things, although they're technically they may say a term, but they're connected to your day-to-day life. And like I said, you see, they are all connected with different parts of your life. Now, let us go to how does NASA come up with all these instruments and measurements and all those things. How do we do it? That is the responsibility of my office, is to come up with technology for future. How do we come up with? As you can see that we invest a lot of money on a lot of projects in NASA. And one of the examples is we started in 2019 to 12, we started developing a 3-frequency horn and a special semiconductor devices which were used to build an instrument which is Tempest-D, which is a radiometer, RF radiometer, and this particular instrument, depending on the frequency at which you measure, different levels of the earth, above the earth cloud levels, you can make the measurement of how much water content is there in clouds. So this was done. We started there, and then as you can see that we launched the satellite in 2015 and 2018, and then in 2021 it deorbited. But that data that it provided, that small technology demonstration, today is becoming more useful, and now MIT Lincoln Lab has transferred the technology to a private company, and they are going to launch 30 satellites, not 1 or 2. Small satellites which will make the measurement. And next one, as you can see that the very first mission, 2003, you can see that it is a big instrument. And by 2018, we had reduced the size of the instrument. 2018, when it was launched, we had made it very smaller. But in 2018 itself, we launched an instrument which is so small. You can see that we are trying to make the instrument smaller, but at the same time, we cannot compromise on accuracy and the reliability of the measurement. We have to also have accurate and reliable measurement. And because of that CSIM, Compact Solar Irradiation Monitor, now the CEOS, that is the organization that does the standards, they said that we have to extend till it was launched, they were measuring only up to 2,300 nanometers. Now they said that you have to measure up to 2,700 nanometers because of the data that came out of this. They found that it is very important that we do. So like this, the technology has to be first demonstrated in a small platform so that it can be put on a bigger platform. And this one, like I said earlier, the radiometer, and along with that, we launched a Ka-band small radar on a small CubeSat. Tiny CubeSat had a radar with a 0.5 meter dish antenna attached to it. And because of that, you can see that these long lines that you see here, the tall poles, these are made by RainCube. And the flat things that you're seeing there, it was made, these measurements were made by Tempest-D. So we can get multiple angles, like you can see cut across as well as you can layers, you can see the data. This is very important. And till then, there was no measurements that was made. 2 satellites we launched together. Just by chance, we happened to launch it, and we made the measurements together. So that led to a whole new mission. Now it's called INCUS, and INCUS is a full mission which has 3 satellites, and each one has multiple instruments, like what I showed you earlier. It was one instrument, but now we have multiple instruments, and which can measure. The idea is that when first satellite to second satellite is 90 seconds, second satellite to third satellite is 30 seconds. The idea is that when it is flying over a cloud, how the cloud is changing within that time. And you can see that the dynamics, how it is changing. Cloud dynamics is most important to study how the storms and all these things happen. And tropics, this is similar to what I showed you earlier, the layers it takes. And this is the one which is now commercialized. And they will launch 30 of these satellites. And 30 of these satellites will be producing a lot of data. And you can see that we have, right now we have 5 satellites. Out of that, 4 are in equatorial. You can see that they can take data so often that when a storm is forming, you can really see how fast it is forming and how it is forming. That is very important to predict what is going to happen next. Then next is HARP. This is again, we flew a small CubeSat, a polarimeter, and then we took that same exact design, same thing on PACE. Earlier I showed you the PACE. On PACE mission, there is a polarimeter just like that. That looks at, again, phycoplanktons. It's a polarimeter. And as you can see, it is on the PACE mission. Then another important thing that at least I pay a lot of attention to is that this is the next mission that we are building. It is called ACMES. It has, as you can see, it has 3 instruments: PLADE, FINIS, and HITI. HITI is a version of an instrument, thermal instrument that we built earlier with the Hawaii, University of Hawaii students, and then we launched it, first version, and second one is going to be on this mission. But when you see PLADE and FINIS, these 2 are student missions. Students are building these instruments, and students will be testing those instruments. The students will be responsible for operating those instruments. And this is an education opportunity. You can see that in Utah State University, there's a class, Space Mission Design course. And the students of that course made this whole thing. And as you can see that this is the whole class. These are the students, and the last two students here, first one, he did the thermal management, and the second, he is from Brazilian Air Force. He's a captain in a Brazilian Air Force, but he was doing his PhD. He built the Finnish instrument. Next to it is their professor. And this is important. See, the student involvement in future is very important. We need to encourage you all to come. And next one, this is like we are talking about gravity measurement. The future gravity measurements, we can't build and launch big satellites. So we are trying to make it compact. This is a student, again, students from University of Florida and University of Arizona. They will be working on this project, and they will be building the instrument. This is for gravity measurement. And I leave it there, and I hope I was able to at least convince you that remote sensing is worthwhile. And I think I can give you a few minutes for questions too, because I'm sure that I have confused you all enough. At least you will have some questions. Don't hesitate.
Hello, sir. So I'm Krishna. My question is, what spectrum of light other than the infrared NASA generally uses for remote sensing?
What?
What spectrum, like the infrared rays are very much used. Other than that,
we use all the way from, you can take from 1 micron, that is the short wave, all the way to 12 microns, 1 to 12 micron. Looks like they're all scared. Ujjwal, you're scared. Yeah, right here. Wait, let them get you the microphone. So.
Yeah, it's not really related to GRSS, but how did you get to this stage? You know, like we're all students right now. All of us want to work at NASA at one point. At least I do. So how did you get to this place? Like that matters a lot.
Back in the time when I got into it, was a lot easier.
Okay.
Because I went as a student to United States.
Okay.
And then after my studies, I was working for about a year or so in Intel. But I was not so happy because in India I was at the Tata Institute of Fundamental Research, TIFR, in Bombay, where there is a lot of research being done. And NASA was kind of an interesting place to do research, and somehow I happened to land. But it is not that you can't do it, but what happens these days is that a lot of the NASA research is done at universities. Like I showed you the pictures, universities. Even if you go to a US university, you can be part of NASA missions. And you don't have to be working at NASA, but you can be part of NASA missions, and over time, you may be able to get into NASA itself. And one thing I can tell you, most important thing is, there's no substitute to hard work. There's no shortcut. You have to do hard work, and you have to be willing to explore new things.
Thank you.
Do we have any more questions? I have a final question.
Oh man, professor is asking a question, then I have to be scared.
Maybe quickly you can cover the life cycle of how the satellites are designed and the process quickly.
Yeah, like I told you, the most important thing, first thing is that the technology. One thing is that we in NASA, in US, we have National Academy. National Academy publishes every 10 years a decadal survey. And in the decadal survey, earlier they used to say exactly this kind of mission you have to do, this kind of mission you have to do. But since last one in 2017, what they did is that this measurement is important, this measurement is important, this measurement is important. So when they said the measurements, then what happens is that at that time, we know which technologies are needed. And it so happens that we, at my office, we always have technology. We don't look at 10 years. We do look at even further more, 20 years or so. So we would have the technology. So once the technology is there, then we do also some things like validation. You saw that INCUS came out because of validation. Otherwise, the bigger missions, what happens is SBG, for example. There is a need, there is a requirement for the measurement. First thing that you do is that, what are the requirements? You have to come up with full requirements. And next thing is there a technology that can make those measurements? If there's a technology, what is that technology? And if there's something new need to be developed, that has to be planned. That's why there are pre-phase A, phase A, B, C, like that. There are different phases. Phase A is when you resolve all the conflicts, like what measurements need to be done, what technology is available, how we can put together all these things. Is it possible to? How much is it going to cost? Do we have the budget? All those kind of things will be. Phase B is when you implement all the technologies, build the instrument design, and all those things will take place. And then C is when you build the instrument and launch it. D, E, and all are operation. Does that answer your question? Any more questions?
Hello, so my name is Dhruv. Regarding that slide of those phytoplanktons, are those blooms environmentally okay for the environment, or does it harm marine life or whatever?
I didn't follow your...
Those phytoplankton blooms, one of those slides. So is that good for the marine life, or is that bad?
There are different kind of phytoplanktons. There are ones which are poisonous and ones which are useful ones. And useful ones are the ones which we need. That's why we need to study the phytoplanktons. If there are bad phytoplanktons that are spreading, we should know that, and we should curb that spreading. That's why we have that PACE mission. In the PACE mission, we are able to look at Oman. You saw that those are useful ones. And as I said, 60% of the oxygen has to come from them. And in fact, recently there was a study that was done. Deep under the sea, there are minerals which, without any sunlight, nothing, the minerals are producing oxygen. They are decomposing hydrogen and oxygen, like electrolysis is happening. And that's why a lot of these scientists are saying that deep sea mining should be banned, because our livelihood depends on the oxygen.
Good evening, sir. My question was how exactly does the mass distribution of Earth, how is it related to the water table exactly?
Water is weight. Water is, it has a weight of its own, mass. It has own mass. There's more water, the gravity is less. So when a satellite is going in the orbit, it moves up and down with the gravity. And we are able to measure that. From that, we are able to coordinate that to come up with the idea of where water table is sinking. And we are since we are continuously measuring, if you had done a measurement 6 months ago, and now the gravity has changed, you know that water table has sunk.
Does that only apply to over the ocean, or also
No.
land?
Land.
Okay.
Even land is more important. Not in the ocean. Mostly, it is water table is in land.
Yes, sir. That's.
Yes, So what I understand is you're constantly, the data is being collected.
Yes.
So it is very important how it is analyzed.
Yes, that's correct.
So analyzing and understanding what is collected is very important.
Yes.
So sir, how do you know what is analyzed is always correct, and it's
There's a big debate on analysis ready data. It's called analysis ready data. When you collect the data, as collected is called as level 0. And level 0, if it is given to somebody, they will not understand what it is. And you need to prepare it to level 1 or level 2. And the process that takes level 1 or level 2 is that you have the calibration data, you have the characteristics of the instrument and all that. Those are all taken into account, and then they are normalized. The data gets normalized, and that is released as level 2 data. And level 2 data, you can ingest it in your models, and then you are able to analyze it. And level 2 data, if you get it from some place like NASA, at least you can trust it. But when a private company does it, when we ask the question, they're not able to answer. Like, how did you come up with level 2? They're not able to. So you have to, as you said clearly, that the data has to be trustworthy.
Yes.
Before you do anything. That is why you need to take the data from trustworthy sources.
Right, sir. And then the next question would be security of the data, sir. You have, how do you?
This is open data. The data is open.
Okay, sir.
Because it has positives and negatives both.
Okay, sir.
Positives is that for greater humanity, everybody, at least United States or Europe, want to put the data as free. The other side of the question is that why would anybody wants to launch a satellite when all the data is available?
Yes, sir.
But that is left to the countries. How do you want to help others?
Right, sir. Okay. Thank you, sir.
Good afternoon, sir. So you said a lot of your projects are done by university students. What skill sets would you be looking for in an ideal candidate?
I told you there are universities, for example, Purdue has a class on mission design. Mostly they are kind of around the problem of reflectometry, GNSS reflectometry. And the one that I showed you, Utah State University, they are doing towards the charge measurement and things like that. So every university has a different theme, and depending on the university you go to and the class that you choose to take could have a different theme.
So are there any online resources you could take in order to...
We are in the process of GRSS society itself is in the process of developing some online resources. On reflectometry, there are already classes that are available online. And we are in the process of putting together a class on a pocket cube. Pocket cube is like 1/8 of the size of a CubeSat. That is a normal CubeSat. Each cube is 10 centimeter by 10 centimeter by 10 centimeter. Pocket cube is 5 centimeter by 5 centimeter by 5 centimeter each cube is. And we are putting together a class. And that particular one will have reflectometry, optical imaging, and now we are looking at adding more functionality to that. And that class is being prepared. Once it is online, I'm sure that Professor Ujjal will be able to guide you to that.
Thank you, sir.
In fact, there are at least a couple of universities here in Bangalore which are building CubeSats already, but they are building regular CubeSats. And I'm sure that ISRO has some student programs.
Any more questions?
Yeah, one more question.
Sir, this, we have this agency, NRSA, National Remote Sensing Agency.
Hyderabad.
Yes, sir. Is that also connected with all this research?
They take a lot of the data from, they are responsible for taking the data from ISRO and distributing that. Their job is, but also they do take NASA data also. They do have a ground station, they do receive the data from NASA satellites, and NASA satellite data is distributed to them also. Even including companies like Amazon and Google, they take the data from NASA and store it where people can use them. In fact, Google Earth uses, today when you go to Google website and they have a Google Earth picture, when you see in the map,
yes,
that is nothing but Landsat data.
Okay. Thank you, sir.
If anybody is shy, I'll be around for another 10-15 minutes. Please feel free to come and ask me any questions. Thank you.
Thank you for insightful words, Dr. Sachidananda Babu, and also thank you for answering all of our questions. I would now like to call our director, Dr. Jagannath Karodi, to felicitate our chief guest. Now, I would request our General Secretary, Sampreet Biali, to come up on the stage and deliver the vote of thanks.
Ladies and gentlemen, good evening. On behalf of IEEE GRSS MIT Bengaluru, it is with great pleasure that I extend my heartfelt gratitude to all those who have contributed to making this inauguration event a resounding success. Today marks a significant milestone as we gather here at Manipal Institute of Technology, Bengaluru, to inaugurate the IEEE Geoscience and Remote Sensing Society. This occasion not only celebrates our commitment to advancing knowledge and innovation in the fields of geoscience and remote sensing, but also reinforces our dedication to fostering a vibrant academic and professional community within our college. We are deeply honored to have had the esteemed presence of our chief guest, Dr. Sachidananda Babu from NASA, whose expertise and insights have undoubtedly inspired us all. His presence here today underscores the global significance of the work we aim to accomplish within the IEEE GRSS section. I would also like to extend our sincere appreciation to our college director, Dr. Jagannath Karodi, for his unwavering support and vision in establishing and nurturing platforms like IEEE GRSS, which enrich the academic experience of our students. A special thanks to our IEEE Student Branch Advisor, Dr. Balachandra Achar, and the IEEE GRSS SBC Advisor, Dr. Ujjwal Verma, whose guidance has been invaluable in steering this initiative towards success. The journey ahead for IEEE GRSS MIT Bengaluru promises to be one of the collaboration, innovation, and excellence. Through this platform, we aim to empower students and researchers to explore cutting-edge technologies and methodologies in geoscience and remote sensing. I would also like to express my gratitude to all the office bearers, members, the administrative, IT, and housekeeping staff who have worked tirelessly behind the scenes to organize this event seamlessly, and I would even like to thank Dr. Shweta for her support towards the smooth flow of the event. Last but not the least, to all the attendees, thank you for gracing this occasion with your presence and for your enthusiastic participation. As we conclude the ceremony, let us capture this moment with a group photo to mark the beginning of a new chapter for IEEE GRSS MIT Bengaluru.
Everyone, please come